National Weather Association's October installment of Webinar Wednesday. Hopefully those of you who attended last month's annual meeting have recovered fully. I think I have, but I'm not 100% sure yet. My name is Becca Mazer, and I will be your host for today's webinar. So a few logistics before we get started. All attendees will be kept on mute for the entirety of the talk. We will certainly encourage you to ask questions or make a comment to our speakers, but please do this using the questions GUI or raise your hand feature on the GoToWebinar, or ask your question on Twitter using the hashtag NWAWebWed. I will then read the questions and comments at the end of the presentation. You can follow along with the presentation on Twitter as well using the same hashtag NWAWebWed. There we go. Or follow the NWA account at NWAS. Lastly, this webinar is being recorded for later viewing. All right, I'm pleased to introduce our speakers for this month. Luke LaBelle is a senior at the State University of New York in Albany, and Jarrett Rogers is lead forecaster at the National Weather Service in Phoenix, Arizona. They will be talking about a machine learning approach to severe thunderstorm downburst prediction across Phoenix, Arizona. And without further ado, take it away, Jarrett and Luke.
All right. Hello, everyone. My name is Luke LaBelle, and as mentioned, I am a senior undergraduate student at the University of Albany in Albany, New York. This research that we're going to be presenting today is from a summer project that I did at the National Weather Service Phoenix as part of the Hollings Scholarship Program, and Jarrett was one of my mentors on this project. So I'll go ahead and turn it over to Jarrett so we can get started.
Thanks, Luke and Becca. As Luke mentioned, he was a Hollings scholar for us this past summer. He did amazing work for an undergraduate especially. So we're really excited to show this work that Luke's produced here. So we'll go ahead and get started. Okay, so the first thing we'll talk about is why did we take on this project? Why is it interesting? At first glance, it looks like, it's just another local study that would be applicable maybe just to Phoenix, but in reality, I think this methodology, especially using a machine learning approach, could really be applied anywhere in the country for a variety of weather phenomena. For this specific study, we looked only at severe thunderstorm wind events for Phoenix. If you know anything about the climate here, especially during the monsoon, severe thunderstorm wind events are pretty much the main hazard outside of flooding that we experience during the monsoon, and they're very difficult to warn on for a variety of reasons. Mainly due to the small spatial and temporal scales that they occur on. They're usually pulse-type thunderstorms that produce localized strong to severe wind gusts. With the tools that we have currently, including just the regular suite of tools, radar and satellite, but also some of the algorithms like ProbSevere, the verification statistics have been fairly poor, especially compared to other parts of the country. A lot of this could be attributed to the lack of population, or maybe the way the population is distributed across the Phoenix area and across Arizona. And I'll show that here in the next slide, or maybe some systematic issues that we're not accounting for. But the goals for this study are to identify both radar and environmental predictors that would help improve the detection of severe thunderstorm winds from cellular thunderstorms in advance, and also develop a predictive tool that can be utilized operationally, that we can use real time in an operational environment. So talking about the data set that we actually used for the study, we only focused on cellular, generally pulse-type thunderstorm events. We do get multi-cell convection on occasion during the monsoon, but in general, these are the events that really are tricky to warn on from an operational perspective. We only looked at events over the Phoenix metropolitan area for the years 2012 to 2018 for the months of July and August. That's the peak of the monsoon when we get the bulk of our severe convection. 2012 to 2018 was selected due to the availability of dual pole radar data for our study. For each thunderstorm event, we looked at 3 radar frames, and we classified them as severe and non-severe or subsevere. For the severe thunderstorm events, we looked at the local storm reports issued by the Weather Service office here in Phoenix, And that was basically what determined whether or not the storm was severe. We took the 3 previous radar frames leading up to that report. And for, excuse me, non-severe thunderstorms, as a proxy for that, since it's a null case, we just use the maximum low-level reflectivity and use 3 radar frames leading up to that. We also did collect environmental data. Andy Dean from the Storm Prediction Center generously helped us out with obtaining that data. So we use generally the hour within the thunderstorm occurrence for that gridded data to analyze the environment. So the domain for our study, as discussed earlier, actually covered the Phoenix area, but Phoenix is huge spatially. So we defined this based on the density of the population and how it's distributed across the area here. So we took storm reports that occurred within this domain and considered those only. Once you get outside this area, the population is very sparse due to a variety of reasons, whether it's public lands or reservations or so on. But this gave us confidence that if a storm occurred within the domain, we're likely to receive a report. It's not perfect, but the verification statistics should be more robust within this domain. On the right there, you can see, just looking at the storm motions for each case, severes on the left and subseveres on the right, you see there's really, substantial overlap between the 2 population groups. But these storms are moving very slowly on average, generally 10 knots or less, sometimes stronger or faster, I should say. But in general, we're dealing with pulse convection here. The events in our database at the top left here, using my cursor to show, you can see the time of day, peaks relatively consistent with the diurnal cycle, maybe a slight lag after sunset. But right around 0Z, which is 5 o'clock local time, you can see the peak occurs in thunderstorm activity for both severe events and null events, and then drops off pretty quickly into the late evening towards midnight. But in general, most of our events were occurring between about 3 p.m. and 8 or 9 p.m. local time. On the bottom left, we're looking at the time between the first echo was detected on radar and when the report occurred. So this is for severe events only. You can see this peaks right around 20 to 30 minutes on the bottom left there. Can't get my cursor to work. But there are cases when it's before 20 minutes. So if you're a warning operator, you have maybe 10 to 15 minutes, in some cases, to make a warning decision, and the storm's rapidly developing. So you can kind of see the motivation behind the study, why these are difficult to warn on, I should say. On the top, the right here, this plot just shows the frequency of severe and null events by storm type. So we categorize these into 3 different classes. The first was discrete with a neighboring cell. So maybe there was some interaction from the neighboring cells, but maybe not necessarily directly affecting the evolution of the storm. The middle was we classified as a cluster, so maybe it's a storm embedded within a broader cluster of storms. And on the right was just an isolated discrete pulse storm. So you can see how this varies between severe in yellow and blue for subsevere. All right, so that's an overview of the database. I'll talk about the environmental characteristics briefly. The main point here is that there really wasn't much difference looking at an environmental perspective between severe and subsevere cases, but I'll go through some parameters here that we selected. Looking at CAPE on the left, most unstable CAPE, you can see there's very similar populations between severe on the left and then subsevere on the right, with the median value right around 16 or 1700 joules per kilogram. SIN showed very little similarities between the populations as well. Maybe, slight, which is kind of counterintuitive, but a slight favoring towards higher SIN for the severe cases. Downdraft CAPE showed a little bit higher mean and median values for severe cases compared to subsevere cases. And since we're dealing with strong to severe thunderstorm winds in these cases, that's what you'd expect to see. Precipitable water populations were very similar, maybe slightly lower for severe, but probably not statistically significant. Looking at various low-level mixing ratio parameters, you can see that actually, there was a drier bias for severe cases when compared to subsevere. This is also somewhat counterintuitive, but if you think about it from the perspective of more potential evaporation in the boundary layer, maybe that could produce stronger wind gusts beneath the thunderstorm base, then that could perhaps make sense. On the right, looking at wind shear, again, we're dealing with weakly sheared environments, pulse convection. So generally similar between subsevere and severe, ranging between about 10 to 15 knots for most cases. A few other parameters that we looked at, 500 millibar temperatures were very similar between severe and subsevere. 700 millibar wind speeds, should be well correlated to the shear values we looked at, and they are. Not much difference there either. And looking at some of the lapse rate, 0 to 3 kilometer lapse rates on the left. So we're looking at 0 reports, so basically null cases. 1 to 2 reports associated with a single thunderstorm, 3+ reports, and then all severe on the far right. So you can see there is some trend. If you could use the number of reports maybe as a proxy for how severe the storm is, which may not be perfect, but you could see that in general, stronger 0 to 3 kilometer lapse rates do tend to favor severe cases with more reports. So again, that, like I just talked about, that may enhance the wind potential out of thunderstorms as well. So we did note some difference there. For Downdraft CAPE, a similar trend as well. So for the 3+ report cases, we had Downdraft CAPEs a little bit higher than for 1 to 2 reports and the null reports as well. So in summary, just looking at all the environmental parameters, just to give you an idea of what cases, what the environments were for all of our cases in our data set. Just in general, the MU CAPE range between, around 1,300 to 1,900 joules per kilogram, and PW is between 1.6, 1.9 inches. So we're dealing with really a pulse type environment with moderate instability, pretty decent tropospheric moisture as well, but not anything that would support multicellular convection. So in summary, for the environmental characteristics, before I pass it on to Luke, we did find maybe some difference in the low-level mixing ratios and the low-level lapse rates as well, and there may be some relationship there with storm longevity and intensity. But in general, environmental attributes weren't really a good discriminator between severe and severe cellular convection. So with that, I will pass it on to Luke, who will get more into the radar characteristics and the machine learning parts of the study.
All right. So as Jarrett just mentioned, there really wasn't much useful in the environment to help us discriminate between severe and subsevere thunderstorms. And that wasn't necessarily encouraging to see, but it means that, a lot of the differences, if there are differences, are going to be present in the radar characteristics of the storms. And so now I'm going to talk about some of the characteristics we see for some different radar attributes before evolving into the machine learning discussion. Just a reminder as to how these radar characteristics were collected, because I think that's important to keep in mind when conceptualizing these results. Again, I collected 3 radar frames for each event. For severe thunderstorms, these radar frames were the 3 frames preceding the first report. So that allows us to get an idea of how thunderstorms are evolving before they produce wind damage. And for subsevere thunderstorms, again, I used the radar frames preceding and including the maximum low-level reflectivity. That's just one metric to essentially try to capture these subsevere thunderstorms at their peak intensity. And so the goal is to be able to separate, what separates a severe thunderstorm from a strong but subsevere thunderstorm. To collect these attributes from these radar frames, I use GR2 Analyst, which should be kept in mind. A lot of these results are going to be most applicable to GR2 Analyst, but I think they can probably be generalized over a lot of other information sources as well. And also, these attribute values were manually collected, which I'll discuss more later. So to go through the radar characteristics, we're going to see a lot of plots like these, just to summarize the results. And so I'm going to take a lot of time on this first one, 18.5 dBz echo top height, just to go over what these plots are showing and how you can interpret them. So first of all, echo top height is essentially a measure of how tall the storm is. And it can also be thought of as a metric for how intense the storm is, how deep and intense the convection can be. And so in this plot, we can see that there are 4 box plots. The first one I'll mark out on the right is the distribution of echo top height values for all of our sub-severe thunderstorm cases. So this gives us an idea of what an intense but sub-severe thunderstorm typically looks like in terms of echo top height. The other 3 box plots all show characteristics of the severe thunderstorm cases. The leftmost is 3 radar frames before the report. This one is 2 radar frames before the report. And then this one is finally 1 radar frame immediately preceding the severe wind report. And so what this allows us to do is to get an understanding of how thunderstorms are evolving prior to producing severe wind. And so in terms of echo top height, we can see here that there's an increasing trend in time with echo height leading up to the severe report, and also that values become fairly well separated from our null or sub-severe events. And so this is an encouraging signal that if you see rapidly increasing echo tops to values above and approaching 45,000 feet, that might be a signal that severe wind is likely to be occurring shortly. So that's the way to interpret these plots. So now looking at this next one, maximum VIL, or vertically integrated liquid. This is essentially a measure of how much precipitation or water is suspended within a storm, and it's another measure of a metric for storm intensity. And so what we can see here is a very similar trend, where there's an increasing trend in with time in vertically integrated liquid up to the report time, and values again become elevated relative to the null events, the sub-severe events. And so this is encouraging again that VIL might be something that's useful, especially on short time scales. Well, we're talking maybe 2 to 1 frame before the report is received, to indicate when severe thunderstorm wind is likely to occur. These aren't the only 2 attributes we looked at. We looked at quite a few more. And so here's another pair. This is the maximum 50 dBz echo top height on the left and 60 dBz echo top height on the right. And we can see that not all variables show the same trend. For example, 50 dBz echo top heights are maximized 3 frames before the report before a slight decreasing trend is evident. And also at all 3 radar scans, these values are higher than our null event distribution. And so what this indicates is that the 50 dBz echo top height might be useful at long lead times to indicate what thunderstorms are likely to produce severe winds. And the 60 dBz echo top height is similar, where we see an elevated distribution, especially 2 and 1 frame prior to the report being received. And so what this is indicating is, again, taller and more robust updrafts are more likely to be associated with severe thunderstorms. Some other interesting results that we found are in these 2 variables here, the height of maximum reflectivity and the height of maximum KDP. The maximum reflectivity one is probably the easiest to interpret. That's going to be maximized where there's a lot of precipitation located in the storm. But KDP measures a similar thing in that it's a measure of liquid water content. And so where the maximum KDP is located, that's where we have intense precipitation cores associated with high liquid water content. And so it's maybe not surprising that both of these show a similar trend, which is to be elevated 2 and 3 frames prior to the report before crashing down towards the surface 1 frame prior to the report. And so this indicates that in these thunderstorms that are producing severe winds, they have high reflectivity values suspended at high altitudes, preceding the wind damage that then starts to collapse towards the surface. And this is in agreement with some previous research on this topic, which lends some support to these results. A couple other important variables that we looked into were the probability of severe hail and the maximum estimated hail size, both from GR2 analyst. And what we can see is that this variable in particular was very good at distinguishing between our severe cases at all radar frames and our sub-severe cases, both for the probability and for the maximum estimated hail size. And so this was a very good indicator as to what storms were likely to produce severe wind, and also again at long lead times, which is very encouraging. So we had some of these variables that were encouraging and showed results that there are differences between severe and sub-severe thunderstorms, but not all variables show the same correlation. And so on the screen now, I have plotted storm size, different metrics of storm size. The major axis length, as I have schematically down here, is essentially how long the storm is in the longest axis. And then the minor axis length is an axis perpendicular to that. And so together, these give an idea of the area that a storm covers. And so what we can see is that there's a much more noisy picture here, and there's a lot of overlap between the distributions, especially 1 and 2 frames before the severe report. And so while storms are growing with time, this isn't something that necessarily should be considered. And I think that's something that is probably known as well. So this is a good sanity check too. Storm size isn't telling you much about the potential for a storm to produce severe winds. It's also interesting to note that at the 3 frames before the report, almost a quarter of the storms did not have any major minor axis length, meaning that they essentially had little to no surface reflection. And so what this indicates is that a lot of these storms are rapidly developing from no indication at the surface all the way to these larger intense storms producing severe winds within just a time period of 2 or 3 radar frames. Some variables that you might think would be useful but aren't show up here: maximum reflectivity values and maximum low-level reflectivity values. In both of these cases, there's a lot of overlap between the distributions. And so it's difficult to use something like the maximum reflectivity in a storm to determine whether it's likely to produce severe. And the indications are not as clear as things like echo top height and vertically integrated liquid that we looked at previously. And then finally, here are 2 examples of things that are just totally not useful. I'm going to focus on this one on the right, the maximum low-level velocity. What this is telling you is that looking at the velocity field doesn't provide much information as to what storms are likely to produce wind damage before the downburst is occurring. And at that point, it's almost too late to issue a warning. And so a lot of the other reflectivity and derived variables are going to be more useful at giving you lead time in predicting when severe winds are likely to occur. And so in summary of all of these radar characteristics, it's encouraging that many radar attributes do show correlations in our data set with the occurrence of severe weather. And this is true at both short lead times and at long lead times. So there's different variables you can look at to try to capture different storm trends. And it's encouraging that these variables are also likely capturing different attributes of the storm that precede the production of severe winds. We also found that some of these radar attributes were not useful. Some like maximum reflectivity, that was a little bit of a surprise. And some like storm size, it was maybe a little bit less surprising. And these results that I presented here were all summarized as part of my project in what I called a quick reference guide that I was able to give to forecasters at the end of my project. And so all these distributions and ways that you can help visualize what a storm is like are available to forecasters, which is an exciting result of this study. So now that we have the context of our data set, what the environment was like and what the radar variables were like, we can now jump into our machine learning model. So for those who aren't familiar, machine learning is essentially a group of techniques that allows computers to discover knowledge. And it's been applied to many different problems in atmospheric science, including this very problem of severe thunderstorm prediction. I think the novelty of this approach is that we're focusing specifically on one type of storm and on one regional domain. And so focusing specifically on the needs of a specific National Weather Service office. The specific random forest algorithm that we're going to be using is, or the specific algorithm we're going to be using is called a random forest. A random forest is essentially a group of decision trees that allows you to predict a class of a storm. And so we're going to be trying to predict, is a storm severe or is a storm subsevere? To better examine how machine learning works, or how the random forest algorithm works, I have it documented schematically on the screen here. And so this would be an example of a 3-tree forest. So you have 3 different decision trees. And so if you have a new thunderstorm case, you would pass that new thunderstorm case to all of these different trees. And at each of these little nodes here, the condition is tested. So for example, is the severe hail, or the size of hail, greater than 0.5 inches? If it's yes, you go to this one and say, is the VIL greater than 20? And if it's yes, you then get to your prediction. And so for each tree, a prediction is generated. And then the majority prediction is used as the final overall prediction by the model. And so in this case, schematically, I have 2 of the trees saying it's going to be severe, 1 saying it's not. And so this generates a prediction. The power of the random forest as well is that it also can be used to generate probabilistic information as well. And so we can see here, we have some sense that 2 of the trees said it's going to be severe and 1 says it's going to be subsevere. So we have maybe a 2/3 probability. And so differences in probability can help you quantify how sure you are that a storm is likely to fit into the severe or sub-severe category. So that's how a random forest works. My random forest used 50 trees with a maximum depth of 2. So I had 50 of these decision trees that were a depth of 2, which is the same as this is here. And I implemented this in Python using scikit-learn. So we knew that we wanted to use this type of machine learning model. The next step was to learn how to use the data, and which was a challenge that we had to address. The data that we had was very complex. We had attributes from 3 radar scans for each case, and we also had the environmental data for each case. And this complexity made it very difficult to use. We wanted this model to be as easy to use and as quick as possible to use, and so it doesn't make sense to use all of this information if it's only going to add time and difficult, or make the model more difficult to interpret. And so the solution to this problem was to identify only the most important predictors and use those to develop the model. One other really nice thing about random forests is that this is done automatically. They automatically calculate what variables are most important to the model. And so after training a model on the entire data set, we were able to isolate only the important things and use those moving forward. And so this list here is what those important variables are. And as you can see, they all make sense based on the discussion we had earlier. Things like echo tops and VIL, we saw them rapidly increasing with time before the severe report. The POSH and MESH, we saw them both elevated for all 3 radar scans preceding the report. And again, we had our trends in 50 and 60 dBz echo top heights as well. And so these are the variables that we wanted to use for the model. I ended up not using the probability of severe hail and the maximum estimated hail size because those are both first really well correlated, and also in the implementation of GR2 Analyst I used, it didn't automatically adjust the environments. And so I wanted this to be as applicable to a variety of data sources as well. So for the final model, I used echo top height, VIL, 60 dBz height, and 50 dBz height. And so we can then train our model, but before we use it, we want to make sure that it actually works. And so for this final part of my talk, I'm going to be talking about how we validated that this model performs, what are some maybe issues with it, and how we can use it moving forward. And so the first validation I'm going to share is called cross-validation. Cross-validation is essentially a way of repeatedly grouping the data, training the model on a large part of the data and then testing it on a small subset of it, and repeating that until every part of the data has been used as a test set. And so essentially this is a way of making sure how the model would work on other parts of the data without training it on that data itself. So it's a way of testing how the model would work in the real world. And so these are the results from cross-validation. And so I'm going to focus on this plot here on the bottom right. What this plot shows is the distributions of probabilities output to individual radar scans by my model. So for sub-severe thunderstorms on the left and severe thunderstorms on the right. Each dot represents an individual radar scan. So for example, this radar scan was a sub-severe thunderstorm that had a probability from my model classified at around 0.36. And so what we can see is that the severe thunderstorm cases, most of them did have probabilities assigned of more than 0.5. So this was really encouraging that our model was able to identify radar scans that were within 3 scans before the severe report was received. And similarly, for our sub-severe scans, we can see that most of them had very low probabilities, which is encouraging as well. There are false alarms, which there always will be, especially when you're using severe reports to verify if damage occurred. I definitely wouldn't be surprised if some of these storms, although I classified them as sub-severe, did produce damage, but it just wasn't reported. And so that must be kept in mind. But also, there might just be issues in the model that we can tease out further as we continue this analysis. So that was the first way I validated it. The second way was to test it on a specific set of years. So again, our entire data set was composed of thunderstorms from 2012 through 2018. So in this case, I took those 2 years out of the data set, trained it on the other years, so trained my model on 2013 through 2017 cases, and then tested it on the storms in these years. And so these are the results we get from that. So again, this plot on the right is the same as the one on the previous slide. What this is telling you is that, again, the model did a very good job at identifying the severe thunderstorms as likely to be severe, which you can see here. And also did a good job at identifying that subsevere cases had low probabilities of producing severe wind. There again are false alarms, which remains an issue, but it's worth mentioning that overall the model again did a very good job at separating these two distributions. On the left, we have the same plot, but instead of all the severe reports being grouped together, we have it separated by radar scan. So this is the model output for scans 3 frames before a severe report, 2 frames before a severe report, and 1 frame before a severe report. And so what we can see is that the model actually did well even 3 scans before the report, identifying what storms were likely to produce wind damage. And so combining those, we can dive in a little bit to how this model performs with some more robust statistics. And so the plot on the right is a little bit noisy, but I'm going to walk through what all the lines on here means. So first of all, we're going to focus on this black line here. This is the probability of detection from the model. And basically what the probability of detection is if you go to this probability threshold, for example, how many of the severe scans will be above that. So what percentage of the severe radar scans are classified as severe using a 0.2 probability threshold. And so if we use 0.2, we get a probability of detection of about 90%, indicating that that would detect around 90% of the severe thunderstorms. And so if we look at 0.5, which is our official threshold, we can see that the probability of detection is around 0.66, which I'll jump to this slide. So that means using this probability threshold, about 2/3 of the radar scans are identified as severe. And this is really encouraging because if we have 3 radar scans per event, that means multiple radar scans on average for each severe thunderstorm event are being classified as severe as my model. And so this signature of several scans in a row of being classified as severe lends credence to the fact that a thunderstorm is likely to produce severe wind damage. This red line right here, this one down here, is the false alarm rate. And essentially what that indicates is if you were to use a given threshold and classify everything as every radar scan that gives a probability above that as severe, how often would you get false alarms? And so for 50%, our false alarm rate is around 0.56. And that seems high, but if we consider that there are more subsevere scans than severe thunderstorm scans, what this really indicates is that for each thunderstorm event, each subsevere thunderstorm event, about 1 scan will be classified as severe. And so again, this lends credence to the idea that if you see a thunderstorm trigger my model and several scans in a row as classifying it as severe, that's a good indication that that storm is actually likely to produce wind damage. And then finally, the CSI is a skill score, so it's a measuring how strong or how well the model is performing. And so that's this blue line down here. And so we can see that the skill is maximized right around this 0.5 threshold, which means that 0.5, as I've been discussing, is the best discriminator between severe and subsevere events. So that's a more robust analysis of the statistics, but there's still one final question that we need to address, and that's how the model performs on actual cases. How will it perform if you start considering it from the start of a storm through the end of the storm? And so that's the final validation I wanted to pursue. So this is looking at only the 2018 test cases, how the model would perform if it was used operationally. And so what we found was that for our 2 subsevere events in the 2018 season that I obtained, only one of them was classified as severe, and that was only for 1 radar frame through the entire storm's life cycle. And so what that indicates is that, again, the model does a good job at calling subsevere storms what they are, subsevere. Of the 6 severe thunderstorm events, 5 were classified as severe with substantial lead time, and the 6th one, the one that was missed, was just a really small miss. The next radar scan would have called it as severe. The lead times are all listed on the bottom here, and so we can see that this model did a good job at identifying thunderstorms with, in general, over a 10-minute lead time. And considering how rapidly developing these cases can be, it's an encouraging result that the model was able to provide lead time to warning operations. And so to give an example of how this might look like in operations, I'm going to walk through one storm case from 2018. This is the storm ID 2018-04. It was from August 3rd of 2018. The background here is images from GR2 Analyst, the left being echo top height and the right being vertically integrated liquid, although there's none showing on the storm or on the screen now. And so starting off, this is the time of this radar scan. So the first one we're looking at is at 051 UTC. I have listed the values of the variables that go into the model, and then the output probabilities at the bottom. So at this time, the storm is just developing. It doesn't really have much suspended liquid, no high reflectivities, and so it's given a very small value of 0.1 probability. So jumping now to the next radar scan, let's see how this evolves. So at 056 UTC, so 5 minutes later, we can see the storm is growing fairly rapidly. It now has some pretty high values of VIL and of these reflectivity heights, and so we see a really rapid jump in the probability, all the way up to 0.5. So keep this in mind. The model first triggered that this storm would be severe as 056 UTC. Jumping forward to 1Z, the next radar scan, we can see the storm is continuing to rapidly intensify and now has 45,000 foot echo top heights and pretty insane VIL values. And so the probability shoots up even more to 0.76. Jumping forward one more radar frame, we can see that, again, we have values increasing more, again, sustained high precipitation cores, and the probability, again, is at 0.78. And then if we move forward to 108 UTC, this first storm report was received from this cell of homes destroyed. And so what we can see is that, going back, we had our model first classify this storm as severe 12 minutes before the first damage was received, and we had 2 scans saying it was severe with a lead time of around 6 or 7 minutes. And so this is encouraging that the model is able to provide lead time on cases like this with 10 minutes or so of lead time. And so as of now, this model is still existing as Python code, but there are also, it is also available on the quick reference guide I mentioned earlier as these 2 plots. Essentially what these 2 plots do is break the model into 2 parts and display it graphically. So if you have a new thunderstorm case, you could go to these 2 plots and find XY coordinates corresponding to the storm and find the probability that would be output by the model. So for example, if you have a thunderstorm case that has a VIL value of 40 and echo top heights of 50,000 feet, you go to that XY coordinate, which is right here, and you can see that this would be a very high probability that this storm is likely about to produce severe weather. All of the dots on these plots show the radar scans from severe and sub-severe thunderstorms, severe being the black dots and then sub-severe thunderstorms being the open circles. And so what this also allows you to see is how similar thunderstorms may have behaved in the past. So looking at our example again, if we had a new thunderstorm that was around 40, or a VIL value of 40 kilograms per meter squared, and then echo top heights of around 50,000 feet, we see that there's another storm very close by that was classified as severe. And so that might help you gain confidence that the storm you're seeing is actually likely to produce severe weather. And so in summary, to summarize the machine learning part of this, I developed a predictive model, and it's available both as Python code and in this quick reference guide. I'm currently working towards implementing this version as a web interface and also improving on the machine learning as well. So this is still a work in progress. I validated the model several ways, and it seems like it's able to successfully identify and discriminate between severe and sub-severe events, even at relatively long lead times, considering the storm lifetime. And finally, consistent probabilities above 50% may be a strong signal that a storm is about to produce severe winds, but real-time testing would be really useful to confirm that this model can work in an operational environment. I was hoping to get to that last bullet while I was in Phoenix, but unfortunately, we did not have any thunderstorms during my time in Phoenix, so I wasn't able to test it out really robustly. And so with that, that's the end of the presentation, and we would be happy to take any questions.
All right, thank you, Jarrett and Luke, for an excellent presentation. I know that's super, super interesting to someone like myself who's kind of a severe weather geek. We do have a couple of questions. And once again, if you have questions out there in the audience, please share them either via the questions GUI, the chat GUI, or on Twitter using the hashtag NWAWebWed. All right, let's go to our first question here. Let me bring that up. All right, have the authors considered comparing environmental parameters with observed wind speeds instead of storm reports? Perhaps there would be a stronger signal in the environmental analysis when compared with observed wind speeds.
Yeah,
So
that's a good question. You want to answer, Luke? Go ahead.
Sure, yeah, I'll take this one. So that's a really good question, and it's definitely something we considered as well. I'll say that the challenge with that is that we already had a fairly small sample size, and so using only severe wind reports that had an associated wind speed with it would have really decreased the amount of thunderstorms we had. And so it's something we looked into, but with this data set we have, it just wasn't feasible using the number of cases we did. But it's definitely something I think would be worthwhile looking into more in the future.
Excellent. So on one of your graphics, you showed the low level velocity as an radar characteristic as useful as a predictor. I know oftentimes meteorologists who are, say, on the warning desk are looking at what we call the mid-altitude radial convergence signature. So that's more velocity signature in the mid-level of the storm. And as a predictor of perhaps severe winds. So I was wondering if you had a chance to look more in the mid-level of the storm or upper levels of the storm in terms of velocity, and whether or not that had a some sort of predictive skill, I should say.
So yeah, that's another great question. And to answer that, I would say one of the challenges with this project was that we were operating on a fairly short time for this project to be completed. This whole project was done in about a 9-week period, and 3 of those weeks were dedicated solely to trying to collect the data set. And so we had to identify fairly early on what things we wanted to look at, and also keep it in a manageable level where we weren't collecting too large an amount of data that would have prevented us from being able to do analysis. So there's definitely other variables that could be important. One of the variables we did look at, which I didn't present here, was storm top divergence. So if you saw a signal of storm top divergence at the top of the storm, what impact did that have on the probability of the storm to be severe? And we saw that it didn't really come up as a really strong signal. We did not look specifically at the mid-altitude convergence, and that's definitely something that could be looked into more in the future.
Yeah, storm top divergence was another thought on my mind, so I'm glad you mentioned that. Comment, great work, very interesting approach. Another question. Well, first, really interesting stuff. Since the model was trained in the Southwest U.S., would this model also be useful farther east in a more moist environment with less steep low-level lapse rates?
So I really like that idea, and it's something I want to test myself. It's not something I know exactly how it would perform, so I can't give a yes or no answer there. My intuition says that it probably would not perform as well in a different environment. In the Phoenix area, you require a very specific set of conditions to get thunderstorms, which we saw in the environmental data part of this presentation. And so I think with a different environment, different storm characteristics may come up as important. But I also think that this is the power of this approach. If another Weather Service office thinks this is something that's worthwhile, to have an intern do a machine learning approach like this for your specific office, I think it definitely will have use, and you may find different things that are important, across the country. It would be my guess that, for example, Gray, Maine, or Albany, where I'm from, may have different important predictors as Phoenix, Arizona. And so I think it's definitely something that's worth testing.
Well, and that leads to my next thought, or my next question for you is sharing your code. How willing are you to share that? I know you said you've got a lot to work on still, but maybe this could be sort of a group exercise in identifying, like you said, environmental characteristics and radar characteristics in various parts of the country. So, bottom line, is your code in shareable form at this point, or do you want to work on it a little bit more before giving it to other folks?
I would definitely be willing to share it because, again, I think it would be useful across the country. I will say that, nothing that I did was extremely groundbreaking. I used the scikit-learn Python package for machine learning, which does a very good job at explaining how the different models work and how the different functions work. And I came into this project having some experience in machine learning, but just in a class format, not necessarily in the application format. So I think, yes, first of all, I would be willing to share my code, but also there's a ton of resources out there that would help in the development of this project too.
Yeah, understandable. Any last final questions from the audience? I'm not seeing any. One comment that I will make is we did, when I was at the National Weather Service office in Cheyenne, we did I think we had I think she was a Hollings, I'm sorry, he was a Hollings scholar at the time, and I can't remember what program he was with. Anyway, he was a volunteer, and no, he wasn't a volunteer. All right, here I'm talking in circles. Regardless, he did a study very similar to yours on looking at environmental characteristics for severe wind burst signals in convective environments, and didn't find much in terms of anything groundbreaking or something that really stuck out as a definite signal in predicting severe winds. So just wanted to share that so you don't feel too discouraged that you didn't find any, just ta-da or, haha sort of signature that it's difficult. And I think, as we maybe dig deeper into this topic, maybe we will find something in the future. So I just don't want you to feel too discouraged. I think the work that you guys did was excellent, and I think it could have some real interesting implications across all sectors of operational meteorology. So just wanted to share that with you.
Hey, Becca,
All
this
right.
is Jarrett too.
Yeah.
Just one more comment to expand on what Luke said. Even if you're not interested in receiving the code, if there are other offices out there or even outside the Weather Service, people that are interested in pursuing or designing a study similar to this, both Luke and I would be more than happy to help and answer any questions and help along with that process.
That's excellent. Thanks for offering that. Well, I think we are out of questions and comments, so we will end now. So thank you guys for a very, very informative talk, and for the audience for sharing some excellent questions. Thank you as well to John Keys, who was our tweeter for this month. He did an excellent job as well. So that's pretty much all we have. Next month, our webinar will be hosted by our membership and marketing committee, and they will feature a couple of wonderful guest speakers talking about successful mentorship stories. So stay tuned to Twitter and Member Connect for details on that. All right, with that, thank you everybody for attending, and we will see you next month.